Hello everyone, my name is Ni. I'm from the Institute of Civil Engineering at the Technical University of Berlin in Germany, and now I will give you a short presentation about the topic investigation of buckling behavior of re-stiffened cylindrical shell under axial pressure. And here's the contents. We can find the first introduction, and then I will show you the cylindrical fabrication, the measurement of geometrical inflection, and then we made some and test and numerical simulation to study the buckling behavior of re-stiffened shells, and another is the conclusion. And here uh, we know that the re-stiffened can be used to prevent the local and global buckling of shell structure, and here you can find some real structure with re-stiffener, but until today, the beneath of re-stiffener just has a neutral attention. And from previous study, and we can find in this diagram, um, the axial load bearing capacity will be increased with the ring pyramid. This means that when we have more ring stiffener, we can get more bearing capacity of shell structure. And before the pyramid study on this topic, we see we may we need to make some experiment to check or to verify the numerical mode and uh, the numerical result. And so we made some specimens from the stainless steel, and the diameter is about 1.6 meter, and the thickness is just 1 millimeter. And here you can find we welding the two half circular shell together, and um, with the normal welding, such as a custom metal acrylic welding process, will cause a very rigid deformation, and this is not acceptable. So we use the so-called cold metal transformer welding technology, and it has a very low energy input. The energy input per unit length is here just about 18 joule per millimeter, and we use the rectangular profile as a re-stiffener here. You can see it is the 8 minus multiplied 8 millimeter, and is the welding on the surface of the specimen with the spot welding process. And the uh, distance between the two stiffness is about 98 millimeter. This is value is the wavelength of buckling in height direction. And we know that geometric inflection is very important for the cylindrical shell. So in this study, we use a 3D laser scanner, and this scanner has a very high accuracy compared to the traditional method. Is the error of the local measurement is about plus minus 0.1 millimeter, and the error of the whole model is about 0.25. And here we have a relative very large specimen, so one time scanner can we can this specimen can not scan in one time. So at first we need a scan part surface here, as you can see in here. This is about 300 millimeter multiplied 300 millimeter, and this is the control point, and this is the control point that we can connect the all part surface together for whole mode. And the scanning process is need about 20 to half hours. It's very fast compared to the traditional method, I think. And finally, we get about 400 to 500 a scan point for this kind of specimen. And here is the result. On the left side is the result for the unstiffened, and another one is for the uh, re-stiffened. And here we can find the maximum value is on the bottom and the top of the specimen. This is because here on the bottom or the top we have the re-stiffener here to keep the specimen shapes. So maybe here the re-stiffener is not perfect and has a manufacturing error. So, and here is the statistical result. We can find the maximum value for the unstiffened shades about 4.5. Here is the 5.5, I see. But with this maximum value, we cannot use for the geometrical inflection value because maybe we have too large value. So here in this study, we use the mean value as the geometrical inflection value and the first angiform shape, angiform as the shape of the geometrical inflection. And here, then we made some tester, and here showing this is the feed, and first we made the loading plate and the support plate, and here has a three layer, and this is a three layer loading plate can reduce the un, influence of uneven edge of the specimen, and we also made the so-called the pre-loading process, and the specimen was not loaded with 15 kilonewton and then unload before the test, and mm, it can be this pre-loading can reduce the loading infections, and maybe the graphs between the specimen and the node plots can be reduced, and to get the distribution stress or strain distribution of the specimens, we bounded the 16 strain gauge on the surface of the specimens, and here we have the result. It's not perfect, but I think it's acceptable for this is a relative for larger cylindrical shell specimens. And nowadays we use the finite element method to analyze the buckling barrier capacity of the cylindrical shell because the shell buckling problem has a lot of nonlinear problems such as material and the geometrical nonlinear. And so theoretically we have two different approaches. I mean the explicit dynamic method and the normal standard approach with static step. The dynamic method has a very high robustness, and it can calculate the buckling and the post-buckling. But this method need a very long calculation times, and the static step is faster, and need just minimal computing results. But the calculation will be stopped when the buckling appears. And normally the traditional static step, I mean the Newton-Raphson approach and or the equivalence or the Risker approach, it's very difficult to converge until the buckling point. In many cases, the calculation will pass over the point where the negative angle value appears from the mechanical value point of view. The calculation is wrong for the cylindrical shells because we see that when the eigenvalue is negative, the cylindrical shell has already destroyed or has buckling. So in this study, we use the so-called accompanying eigenvalue analysis to calculate the nonlinear buckling load at first in a general static calculation. With the material and the geometrical nonlinear where analysis is carried out and based on the nonlinear result, the linear eigenvalue calculation will be solved for each increment. And in this is a study, we use the abacus with the restart analysis to get the theoretical load at each increment, and with this is Python script in abacus, we can automatically get the relative exact nonlinear buckling load. And here in this slide show the results. Here the left one for the unstiffened shell and this one for the stiffened shell. And the difference between the experiment and the numerical here is about 6% and here it's 13%. But anyway, we can find that the ring-stiffening can increase the barrier capacity of a cylindrical shell. And for this is specimen, ratio to the ratio of the radius and thickness is about 800, and we can find that with the 5 re-stiffness, the barrier capacity can be from 117 to 418, and this is increasing is about 215%. And last, we also check the post-bargaining behavior with the dynamic approach, and here we can find the collapse shape from the numerical result is more or less similar with the experiment. And at last is the conclusions. And at first, the 3D scanner technology can be used to get the geometric infection of the shell, and the numerical calculation based on the accompanying eigenvalue analysis can be used to get the buckling load of the cylindrical shell, and the result showed the ring-stiffening can be increased the barrier capacity of cylindrical shell. And for the future work, I think maybe we need to discuss the influence of real geometric infection and the welding process maybe. And we also find a good method to directly input the geometric scan geometric infection direct to the numerical model. And we also made some pyramid studying and give some suggestion for the practice and for the current standard code, co design code. And so this is Outlook is not very timely. So, but anyway, thank you for your attention. Time's over, I think.